Hi, good afternoon, everyone. So this week we will discuss constructive counting. So previously, I believe that we discussed some casework. Casework is the most general or very intuitive way for counting because essentially you look at the big scenario, you try to break down a big problem into sub-problems and handle each sub-problem separately, then combine all your results. But when you do casework, you need to be very sure that the cases that you break in the original problem into, they have to be comprehensive and no just overlapping. So that means that all your cases together should cover all possible scenarios. So there's no undercounting. But your subcases, they cannot overlap with each other. Otherwise, you will have overcounting. So that is really a top-down approach. Constructive counting, on the other hand, you don't look at the big picture at the very beginning. It's more like you build from the ground up. It's more like a bottom-up approach. Okay, so what is exactly constructive counting? This is not a definition, but this explanation is a little bit vague. Says that kind of how many ways you can construct a particular item. So, what does that mean? Well, you want to build a case that meets all your requirements or constraints, but you don't look at from the top. You look at the local things. What constraints you have? What things that you need to do in order to build the case from the ground up. Okay, so that's really, you want to think about how we can construct. What do you mean by construct? You just add all the just arrangement or elements of the things that you are counting until you meet the overall requirement. And that way, you typically will see a way to count them. But still, I agree, this is still in the abstract, not really that helpful. Perhaps a best explanation is to go through some examples. But there's one important thing that you want to kind of just take it as a tip or kind of just a rule, but it's not a true rule. All the counting problems will have certain constraints or restrictions. Otherwise, counting would be really easy if we don't have any specific constraints. Usually, those problems are very easy to do. So in constructive counting, because you're building things from ground up, you want to look at those constraints first, meaning that when you construct things, you deal with the restrictions first. Okay? And this is generally true. If the problem, the numbers are large, the problem too complicated, it would help if you just consider some simpler cases with the number smaller, and by just dealing with them, you can, because the number is small, you can enumerate some cases. And hopefully from such an experiment, you can see the pattern or the strategy of how to count the larger numbers. But this is generally true. For all kinds of just technique, counting techniques, you can use this. You deal with smaller numbers to see how that gives you some intuitive ideas. So without further ado, let's do some real problems. Okay, this is a problem from meaning number 31, and this is problem 7. So how many 5-digit numbers have exactly 10. Okay, what do we need to do? We need to build a 5-digit numbers. If we don't have any constraint, say how many ways you can have a 5-digit number, that's very easy, right? Because the first digit cannot be 0, so you have 9 choices. Then after that, every digit can be any of the 10 digits from 0 to 9. So you would have n times 10. So 90,000. But that's not the case here. There's a constraint. The constraint says what? The constraint says that you can only have 10, but you must have 10. So you have exactly 10 in this 5-digit number. That's a quite significant constraint, but how do we count with this constraint? Well, because there is a constraint here, right here, you have exactly 10, you naturally want to see how we can meet this condition just front on. Just right at the very beginning, we want to address the issue. So you have exact 10, right? Where do you want to put it? This sounds like doing casework, but this is not really casework. So 0 cannot be here. We cannot have a 0 at the very beginning. Other than that, really there's no other additional constraint. So 0 can be put in any of the other 4 positions. And from our counting perspective, it doesn't matter where you put, right? Because the rest is just, we don't make a distinction between the unit digit, the 10th digit, 100th digit, or 1000th digit, because they are all the same for our counting perspective. The only thing we need to worry about is that we need to have a 10, exactly 1, in one of those 4. So therefore, you have 4 choices to put this 0 in. Right? You can only have 10. You have 4 possible cases, 4 positions. Therefore, you have 4 choices. But after we put this 0 down, how do we continue to build this number for the other remaining 4 slots? Remember, out of 4, this 10,000. This 100,000 digit is always there. So, but the other 3 are kind of just in 3 of the other 4. We don't know exactly where they are, and we don't even care. Because at this point, we know all the 4 digits cannot have 0. The first one is just by default. The other 3, because we already put 0 down, with this constraint, we cannot have 0. So they are in exactly the same situation. So each of them will have 9 possibilities. That means from 1 to 9. So the total would be easily you times 4 9s, because they are all independent of each other. So in this case, this problem is very easy. And the way we arrive at this number is we kind of build this 5-digit number up. From the very beginning, we first look at, with that constraint, where to put 0. And after that, the remaining ones, it just kind of like without any constraint. Remember we did 9 times 10 times 10 times 10. If without constraint, that is similar to this part. And in fact, when we do without a zero constraint, we still have a inherent constraint. That is, the first digit cannot be 0. That's actually exactly how we build that as well. So even in that case, we actually use the constructive counting. We first look at how we should count the first digit. There are 9 cases, so that times 9. So this is a good example of showing how you do constructive counting. Okay. Of course, there are other ways of doing that. If you look at the standard solution, you will see a different counting strategy. But That's good to see. There are many problems that are amenable to multiple counting methods. And that's actually one of the greatest things about counting. Because if you count the same thing in different ways, usually you can obtain some identities. Because the two results, while seemingly different because you are taking very different strategies, but they must be the same because they represent the same total count if you count both methods correctly. Okay? All right. Next problem. So my class has 7 girls and 2 boys, so 9 kids. In how many different ways can the 9 students sit in a row of 10 chairs? Okay. So you have 9 students into 10 chairs, but there's an additional constraint. If the 2 boys insist on sitting adjacent chairs, so they are good buddies, they want to sit next to each other, they don't want to be separated by the other girls, which, well, understandable, right? So now, how can we build cases? Well, there are many ways to think about this problem because it's kind of just information rich. First, you have 2 groups of students. One group has 7 identical, not identical, different girls, but 7 girls. The other group only has 2 boys. And together, you only have 9 students, but you have 10 chairs. And that means that you have 1 chair that must be empty. And then you have this constraint that 2 boys have to be just together. So, there are different ways of doing this. We are primarily focused on constructive counting. So, based on we just discussed about constructive counting, how can we construct a valid case? And that way, it will give you, along the way, it will give you the total count. Where shall we start to construct a valid seating case, seating pattern? Well, it seems that this constraint is quite significant, right? 2 boys, they have to sit together. That means that the 2 boys will be something like this. If put in seating, they cannot be separated by anyone. So there's no girl in between. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 chairs. With this constraint, you can cleverly think that this is just one object. You treat the 2 boys always together as a block, right? It's just like maybe a gigantic person that need to simultaneously take 2 seats. That can actually happen. You know, this is not a joke, but if you are overweight and you just fly, the airline company may actually, in some cases, if you are severely overweight, you may be asked to buy 2 tickets because there's simply no space, especially if like coach, you cannot really sit into 1 seat. You may be forced to buy 2 tickets if you are really that overweight. So think about the 2 boys are kind of say they are fixed together. They have to move all together. In that case, how can we position this block? Well, you can only have 9 ways, right? You can start from here, then you gradually shift to the next position, and toward the end. But because you are combining 2 together, so in this case, there are only 9 available ways for this block to be seated. You have 10 chairs, but you slide through, you can never reach 10. So you only have 9 ways to seat this block of 2 boys. So we first write down a 9. But remember, the boys are different. Even they are twins, they are different. So within this block, we have two ways for each of the 9 cases. We have a 2 factorial permutation, right? Because you have boy 1 first, boy 2 second, or boy 2 first, boy 1 second. You have a 2 factorial ways to position the boys within that box. Now we settle with how we arrange the boys. What else do we need to do? Well, we have 8 chairs remaining, and they, of course, they are not necessarily just consecutive, because now you put, say, if the boys are here, the other 8 chairs are separated by those 2 boys. So, but that doesn't matter because we don't really care. Conceptually, you still have 8 chairs. Now you want to put 7 girls in. Okay? Well, for permutation, you can think of it this way. I have 7 different girls. In how many ways the first girl can sit? 8 ways. How many, after that, how many choices does the second girl have? 7 choices. And you continue this until you arrange the last girl, which at that point, the last girl will have 2 chairs to choose because one of them will be empty, right? So even the last chair, last girl still have a 2 choice. So the way to arrange those girls is really this method: 8 times 7 times 6 all the way times 3 times 2. But wait a second. This is actually, while we only have 7 numbers here, the last one is really nothing if times 1, if we get a full 8 factorial, right? In other words, is also we only need to arrange for 7 girls. Effectively, this is the same thing as we need to arrange for 8 girls. If we have 8 girls, we still have exactly the same number of permutations for those girls. The reason this is true is that you can think about, say, that empty chair also as a girl. Well, we just imagine there's another girl sitting there, she's in the empty chair. So the empty chair is the 8th girl. So even though we are only arranging for 7 girls, once you have figure out where to sit those 7 girls, the other empty chair or the last girl, imaginary girl, will be automatically seated. That's actually the same thing, or what will happen if you indeed arrange 8 girls, right? You only need to arrange the first 7. The last one will be automatically put into the final chair. She does not have a choice. So even so, in this case, we are only arranging for 7 girls. Effective logically, it's the same thing as if we are arranging the seating for 8 girls. So that's why, even though we came here, this is exactly the same as a factorial. Yeah, just a kind of little bit, just conceptual gymnastic to how to equate the 2. They're the same. So because this has nothing to do with this, the total number of seating patterns is really just 9 times 2 times a factorial. Okay? So this is how we construct this one. But even after solving this problem, you may still observe this is a little bit interesting, right? We have a factorial, and we have a 9 right before that. We can combine that into 9 factorial times 2, right? This is actually simpler because conceptually this looks cleaner. Is there a way to explain this particular calculation with another way of looking at the counting problem? Indeed, you can. We just say that the empty chair is a special girl, right? But we can also think about the combo, the block of the two boys as another special kid. So now we are truly just say we have 9 kids, 7 girls, a special combo boy, a special empty girl. It doesn't matter. We just want to arrange them in certain order. But remember now you only have 9 chairs because that combo boy will automatically take 2 chairs no matter where you put them. So in this case, you are doing a 9 kids sitting with 9 chairs because the block of the boys will always take 2 chairs. But we are looking at how the permutation will look like. How many ways to arrange those 9 kids in different ways? Of course, it's 9 factorial. And think about given any particular pattern, you automatically expand the block of 2 boys. That's it. You expand it into 2 seats because that's how they do. They take 2 seats. So that way you will go back to 10 seats. However, there's one detail that you cannot forget. That is that within this block of 2 boys, after you figure out the overall seating, you have to consider between those 2 boys, you still have a 2 permutation because they can swap their positions. So overall, that's how you arrive at this 9 factorial times 2, which is exactly the same as here. That's not surprising. And this is what we have been emphasizing for counting. The same counting problem, you can look at it in different ways. In this case, the 2 ways are actually quite close. So that's why one is 9 times 2 times 8 factorial. The other is 9 factorial times 2. Of course, they are equal because the 2 methods share a lot of similarity. They kind of just overlap a lot. That's why the 2 results are immediately obvious equal to each other. But in some other counting strategies, the 2 methods may look very different. Okay? So that way, you will not be able to immediately tell the 2 are the same. But logic tells us that as long as you count either method correctly, the result must be the same because they both represent the same total. So the 2 seemingly very different expressions must be actually equal to each other. Okay, so that's for this problem. By the way, there are other ways to count this one as well. Problem 3, a palindrome number is a number that reads the same forwards and backwards, meaning that they're symmetrical. Symmetrical about a middle thing. If you have A numbers, let's say you have 2 4s, right? So the symmetry point is not a number, it's just an imaginary line. You have 4 numbers on the left, 4 numbers on the right, but if you read this way and if you read this way, they must be the same. Therefore, this number will be equal to this number, and so on. But what if you have odd number of digits? So let's say that we have 1 less. Well, in that case, that middle number itself will be the symmetry of just a point. So in other words, we still have the other pairing, but this number can be this digit, I should say, this digit can be anything because it doesn't have to be kind of symmetrical with another number. It's all by itself. That's how palindrome number works. Now, how many 7-digit palindrome numbers there? Well, we just gave this example, right? This is a 7-digit number. So now you understand the constraint is that how to build this 7-digit number so that we have this match, this match, and this match. Okay. Remember, this is a number, so other than this constraint, we still have an inherent constraint that the first digit cannot be 0. That's true for any multi-digit number. So, with those two, how do we build that one? Well, as with all numbers, our first digit can have 9 choices, right? From 1 to 9. But we immediately see once this is done, we don't have to worry about this guy because it must be the same. So that also gives you the hint that effectively we don't worry about the hundreds and the tens digit at all because they must be the same as this digit and this digit. So we only need to look at the rows. But now, the reason we remove that, we also remove a major constraint. We don't have to worry about that rows crossing lines. So, what other constraint do we have? We don't have any left. We already took care of the first one. It has 9 choices, and the middle one, right there, it has no actual constraint at all. It can be any digit from 0 to 9, whatever you want it. So that means that we only look at the other 3 digits in those places, and each digit can be any of the 10 digits from 0 to 9. No more constraint. So we easily have 9 times 10 times 10 times 10. Does that make sense? We already took care of all the constraints. We took care of the first one by understanding there are only 9 choices here. Took care of the palindrome requirement by removing the last 3 digits altogether because they must match the first 3 digits. And the middle one, it's just all by itself. Therefore, the correct counting is just 9 times 10 times 10 times 10. Alright? So that's really straightforward, but you can see how constructive counting works. You just build things up. Okay? This is kind of in contrast to casework. With casework, you keep a vision from the high level. You look at how you can partition your space into different subcases. And you have to be very careful there. You have to make sure there's no overlapping and no just overlooked cases so that no overcounting, no undercounting. You have to cover the whole space in a good partition that do not overlap. Okay? So that's casework. But constructive counting, we don't do that. We look at the local things, the smaller things to add more additional just thing into the overall structure so that it will meet all the constraints. Okay, next problem. Okay, how many 4-digit positive integers are there such that no 2 consecutive digits are equal? Okay, this is a really good example for constructive counting. Otherwise, think about casework. If you do casework, well, how can you classify all the cases? The constraint here is no consecutive digits are equal. It's not easy to break this down into some cases, right? Because there are too many cases where there's no consecutive, just consecutive to identical digits. There are too many cases. So perhaps a better way is combine casework with complementary counting, where you just look at how many ways you will have at least some consecutive digits. So it could be you only have exactly two, because only have 4 slots here. You have exactly 1 consecutive, or you have 3 consecutive in a row, or you have all 4 consecutive. That do casework. Then do the complementary counting to subtract this from the total possibility. That's one way of solving it, but that sounds quite convoluted. But it's still better than if you have break down all the possible cases where you don't have consecutive two consecutive digits. But with constructive counting, this problem becomes very trivial. You want to have a 4-digit number where you cannot have consecutive digits. So we construct this from the beginning because that's a low-hanging fruit where the constraint can be taken care more easily. As usual, we know the first digit has 9 choices from 1 to 9. Now we want to find the next digit. Usually, if there's no constraint, like we said, this can be times 10. But now it says that you cannot have consecutive same digits. So whatever the first digit is, we cannot have that same digit in this second slot, right? This is the constraint. But that also tells us that how many choices we can have for the second one. Now again, we can only have 9 because we have to exclude that very first digit. After this, constructive counting requires you look at the third slot. But this time, it's still the same constraint. We just cannot have the same digit as the second one. But we could have the one as the first one now. So the very first digit has no more impact on this one because they're not adjacent anyway. So we don't really care. Say this is a 3, this is a 5. We could have a 3 here. We just cannot have 5. Okay? So that means that for this third one, once again, we can have 9 choices. And those 9 choices are not just constraining anyway by the first 2. We already taken care of that constraint by reducing this from 10 to 9. So this continues for the next one as well. So easily, for this problem, we have 9 to the 4th power of ways. And this is perhaps the cleanest example of showing constructive counting in some problems is the best idea. If you want to do casework, this could be really difficult. Okay, it's doable, but it's difficult. Okay. All right. So, you have just how many pairs of distinct positive integers, a and b, both less than 100? So, is ab the square of an integer? Okay, that sounds a little bit more interesting. What does that mean? Well, you want to figure out how many pairs of A and B. Remember, a pair is ordered pair, okay? So AB is different from BA because when we talk a pair, this is ordered. Okay, distinct positive integers. So A and B cannot be the same. If A and B are the same, then A over B would be 1. 1 would be a perfect square, right? So A and B cannot be the same. But in that case, A and B still a perfect square. So that means that we have to think about how we can match this constraint first. Because A and B both less than 100 is just so A and B actually has a range. It's somewhere between 100 and 1/100, right? Depending on whether A, let's just say A is the smallest, A is 1, and the B is 99. So 1/99, that's as small as you can go. But apparently we don't care anything that is a true fraction, because we want to make sure that this is an integer, and it's not just an integer, it's a perfect square integer. But this constraint is significant because it's less than A over B apparently is smaller than 100 because both are greater than 0, at least 1. So the maximum this fraction can be is 100. And how many integers less than 100 that is a perfect square? We already say 1 cannot be the case because that requires A equal to B. So we only have 2 square, 3 square, 4 square, 5 square, and up to 9 square, right? If it's 100 square, this cannot happen. We already know this is less than 100. So that means that the constraint really say A over B can be only by those cases. 2 square, 3 square, up to 9 square. How many of those numbers? 8 of them. 9 minus 2 plus 1. That's how you count how many numbers there from 2 to 9. 9 minus 2 plus 1. So A over B can only be 4, 9, 16, 25, 36, 49, 7, 8, 64, and 81. All those 8 numbers. Okay. So what are we doing here? Are we doing constructive counting? Yes, we are. Also, this looks like a lot like casework. So sometimes the two share a lot of similarity because when you construct things from the ground up, invariably you will involve some casework cases, okay? Because that's just the way it is. So essentially, while we are doing constructive counting, we encountered casework ideas. So that means that A over B can only be 4 and so on. Okay? So if that's the case, how do we do? Well, essentially at this point, we will do casework. Okay? Let's just say A over B is 4. Okay, what can you have? You can have 4 over 1, right? And 2 over A over 2, 12 over 3, and so on, because both A and B are integers, positive integers. So the way to do it is just choose the denominator first, then to see the numerator cannot be over 100. So that way you go through all the way through. If it's 125, so the maximum you can go is 24. You cannot be 25, otherwise you will be at 100. So that is 96. And you just count how many in the just denominator, because that's an easy way to count. So clearly you see 24 for this case. Okay, so the next one would be 9. Exactly the same idea, but this time it will converge much faster. So because the maximum you can get is 11 here, you get 99. So just make sure that you remember what we are doing. We are just to count each rows how to get the total number of possible cases. So this will continue. You can easily see the next will be even easier because now you get to very quickly you arrive at 6. 6 times 16 is 96. If you get one bigger, that will be over. So you continue, you list all of the 8, which will be much quicker. So this would be 3 get 75. You cannot before, otherwise it will be over. So 36, you get actually just 272, right? 3 will be 108. 49, the same thing, 298. And if it's 64, from that point on, you know you only have 1. Because even if you have 2, it will be 128. So that will be 34. For all the rest, this number is just 1. Oops, I should use a different color. So, how many we have already circled? First one, 11, 6, 3, 2, 2. Remember, we have 8 cases. So 1, 2, 3, 4, 5. We already, at this point, we have covered 5 cases. Therefore, we have 3 cases where you have only 1 possibilities. So easily, you have 11 plus 6 plus 3 plus 2 plus another 2. And 1, 2, 3, 4, you have 5 cases. The other 3 cases are all 1s. So that's the total you have. Okay? This is, oh, there's 24, I'm sorry. Oh, shoot. Yeah, there's a 24 there. So we have one less, it's 2 cases here. So because my screen just deceived me, I did not see that one. So you have 1, 2, 3, 4, 6 cases that are not 1, and then you have 2 1 cases, which makes sense. 64 and 81, right? This is 8 square, and this is 9 square, and that's the only thing you have. So the total is 24 plus 11 plus 6 plus 3 plus 2 plus 2 plus another 2. I think this is 30. This is 50. Okay, so you have 50 cases. But although this looks like a casework, it starts from constructive counting because initially we don't clearly see what the cases are. We actually get into casework by constructive counting by looking at this constraint. A over B has to be a perfect square, and we want to build this first. Make sure that we meet this constraint. Okay? So this is how it works. Okay. Next problem. This is from Mini 42, problem number 8. Well, this problem can actually be quite just tricky. You have 7 students sitting in a row of 7 chairs. Well, sounds familiar. Ben insists on sitting next to Amy. Okay, you have Ben, you have Amy. They like each other. Maybe only Ben likes Amy, but Amy does not really like Ben, but Ben insists on that. And Carol insists on sitting next to Dave. I don't know what Dave's feeling is, but we know Karen's feeling, right? Okay, in how many ways can the 7 students be seated? Well, this sounds kind of familiar to a problem that we solved earlier, right? That is the concept of blocking. But you have to remember, once you do that, you have to count the way the 2 persons in the group, they have to just be able to permute. So if you think Ben and Amy as one block, and Karen and David is another block, then you reduce your 7 students to 5 students because you have now 2 combo students. And with 5 students, how many ways you can arrange them, their relative position? You have 5 factorial. That's for sure, 5 factorial. But now here comes the tricky part. For both A, B, and C, D, they should be able to permute within themselves. So A, B, and BA are possible. C, D, and DC are possible. So therefore, you have to times this 5 factorial by 2 and 2. What is 5 factorial? I think 5 factorial is 5, 4. That's 120. Okay, so in this case, it's 480. So in this case, the problem, whenever you see something like this, we do not advocate you memorize tricks. But this is so standard, okay? So when you have something like a seating problem, you have 2 students need to go just together. A natural way to think about this, you have 1 less student, but you have 1 special student, person, whatever. Because now the 2 have to be next to each other. It serves as a special student, but at the same time, if you do that, your total number of students will be 1 less. And the total number of chairs will be 1 less as well, because this special student always take 2 chairs at the same time. So effectively, logically, you only have 6 chairs, and 1 of them is kind of special, but you don't really care. The trickiest part is that don't ever forget, after you do that, you have to consider the relative order within 2. And we can generalize this just kind of standard trick to say, what if still 3 students insist they have to sit in a row? The same thing, you get 3 students in a block, so you have 2 less students, 2 less chairs, but after you do all the permutation calculation, you remember those 3 students, unless you have additional constraint, you will have to times that with a 3 factorial multiplier to your total number of permutation, because within those 3 students, they can, once they have secured their block of 3 chairs, yeah, they are good bodies sitting in those 3 chairs, but within them, they can still shuffle their order, and that is 3 factorial. So you have to memorize, you have to do this. In this problem, though, we have 2 such blocks, and they're independent, right? We have Amy, Ben, kind of just a team, and Carol and Dave, another. So you have to times 2 factorial and times 2 factorial. Okay? All right. Got a lot of problems, don't we? Problem number 6. Okay, so, oh, this is a difficult one. This is not a problem. Okay, all right. So, problem number 7. This is a difficult problem, okay? Meaning number 42, problem number 9. When a single circle joined in the plane, it divides the plane into 2 regions, inside the circle and outside the circle. So if for those of you who have studied a little bit of set theory, you should feel very kind of familiar, right? In set theory, we use this Venn diagram to do a lot of things. So our universe is kind of usually square, but on a paper you may present it as a rectangle, which is fine. This is the universe. So when you have a circle, it certainly divides this universe into 2 portions, right? One inside the circle, like this, and one outside the circle, like that. Okay? So clearly, you have a partition of the total space into 2 portions. Okay? two regions inside the zone. So what is the max number of regions into which you can divide the plane when you have 5 circles in the plane? Okay. This is difficult because once you have 5 circles, your drawing will become very messy. But we need to first understand what we are trying to do. We are trying to see the maximum way, meaning that you want to draw those 5 circles in a way that you create as many additional regions as possible. So when you start, you can. This is another way, just a point when we talk about constructive counting earlier, right? You want to start with the smaller number. You don't want to draw 5 circles all at once because you may easily mess up the drawing, cannot even see what's going on. So let's just say we have 1 circle drawn on this plane. There's no choice. You just draw it that way. And you clearly divide the overall region, the rectangle region in this case, into 2 parts. One inside this circle, one outside this circle. What if now you can add a second circle? Well, if you are not that careful, you can add a circle here. What does this do? Well, it divides the region that is outside the first circle into 2 regions. But is this what we wanted? Look, if you count it now, you'll see. Now we have 2 circles, we have 3 regions. Initially, it's always we have 1 circle, we have 2 total regions. This is not the good way because clearly you can do better by make sure that this circle intersects with the second circle, the first circle, something like that. Well, in this case, you will have 4 regions clearly, right? Because it intersects. The point is that this circle intersects both regions, meaning the original region inside circle and the region outside of the circle, the first circle, they both intersect with this red circle. That's why, because they intersect in each case, so the red circle cuts both original 2 regions into 2 sub-regions. Therefore, in total, we have 4. So think about what this red circle do. It cut the disk inside the blue circle into 2 portions, right? This the first one, and this is the second one. This is completely inside the blue circle. The same thing for the region outside the blue circle. So both cut by this red circle. So clearly, this is the best we can do. Can we do even better, say create 5 regions? Clearly, you cannot do that. It's a circle. Circle cannot cut this intersect any of the 2 regions in the way that it creates 3 regions. The best it can do is to cut each region into 2 pieces. So now, what do we want to add a third one? Well, the third one wants to intersect all of them, right? In this way, it wants to intersect, say, all. Well, I'm not drawing the because of the space limit. I did not draw this well, so perhaps I should use a different color as well. So if the third circle is right here, this is as the best we can do. The green circle intersects with all the 4 regions. Remember here we have 4 now. It intersects, if you look really carefully, it intersects all those 4 regions. Therefore, now we have 8. Okay. So now what is the trick here? If we keep drawing this, it will become really messy. But what is the point of doing all this? what happened? Why the first time when we draw the red circle outside the completely not intersecting with the blue circle, it failed? It's because the red circle did not intersect with the blue circle. And now, what happened with the green circle? It intersected both the blue circle and the red circle. And this can be easily done, right? How many ways the two circles, if we have two circles, they can intersect? They can, no intersection at all. That means that they're completely separate from each other. They can intersect at exactly one point. That means that they're tangent to each other, right? We learn from geometry, this is called tangent. And finally, they can intersect at 2 points. They cannot intersect with 3 points. Why? Does anybody know why? They cannot intersect at 3 points. This can be proven by contradiction. If the two circles intersect at 3 points, then those 3 points belong to both circles. But with 3 points that are not on a straight line, they decide the circle. This is a fundamental result in geometry. As long as 3 points are not on the same line, say they are forming a triangle, there's always a circumscribed circle for that triangle. So 3 points will decide one circle. You cannot have 2 different circles passing same three points. So 2 circles can only intersect at 2 points. So now the point is that if we do this, first we have 2 questions to answer. Each time when we add a circle, can we make sure that it will intersect all the existing circles? The answer is actually yes. You just need to make sure that when you do the join circles, you don't join them in a very kind of just an extreme way. You can keep adding a circle, just so they're all the same. You can keep just moving, shifting a little bit. You can do this indefinitely many times. You can keep adding a new circle that intersects. Just each time, you just shift the circle from the existing one by a little bit so that you have enough space. Because you just shift a little bit, they will keep intersecting all the existing circles. In theory, this can be done because there's no limit to say how separated the 2 circles should be. The 2 circles can be almost identical. Just shift a little bit, but the same circle. Then they will definitely intersect. But you can keep doing this for the new circles. So there are definitely ways that you can add a new circle, and that new circle intersects with all the existing circles with 2 points, not just 1. If it's 1, it's tangent. So that way we know we can keep adding circles, and it intersects every existing circle at 2 points. Now comes the second more difficult question. When you do this, how do you count? What happens when you count? So that really is just a way of understanding what happened. Okay? When you have a circle, let's just say we have a circle. We have not finished this circle. We just draw half or a portion of this circle. It enters this circle, right? At this time, it has only one intersection with this circle. We create one intersection point. But with one intersection, did the cut complete? No. We have not completed the cutting yet because this is still pending. We have not finished it. If you look at this, the red circle is still red circle. It has not been partitioned into two space. That partition will occur only when you finish this portion of the new circle, that it intersects the first cycle again, meaning that this curve will exit that circle. Only when this happens, you create two intersecting points, and there's an arc here. This arc will definitely cut whatever region in that into two. At the same time, those two intersection points, there's another arc outside this circle. It will also partition the outside world into two regions, right? Okay, if that's the case, how do we count? Well, you can see that this is kind of a recursive relationship. When you first have one circle, it has two. When you have a second circle, it adds another two. Where does those two came from? Well, it came from the fact that you have two in the first place. This one cut two into four. Okay? So, for the second two, you essentially add two into those two. When you have three, in this case, you cut all the four into two, so you add another four to get to this 8. Now the next step is very tricky. Shall we say when we add the fourth circle, it will add 8? No. Why? Remember, it's not doubling whatever regions you have. You create a new region only because you cut a circle into two halves. Okay? So that happens in the case that because each circle has an inside and outside, the first time you cut a circle, but it creates two actual space. This time, the second one, you cut two circles. Those two circles happen to have 4 regions. But when you add the fourth circle, there are existing 3 circles. How many endpoints can it create? This time will be only 3 times 2, right? Because you can intersect with each circle by only 2. So therefore, you only have 3 existing circles. In this case, you will be only able to create 6 new regions, because that's how essentially you are counting how many intersections intersection point you have. Each time you add an intersection point, you add just 2 regions. So the number of regions added is actually equal to how many new intersection points with those circles you can create. So in this case, when you add the 4th circle, it can only create 3 times 2 new intersection point. So you are adding 6 new regions. And finally, for the 5th one, now we have 4 existing circles. It will cut into those 4 circles at 4 times 2, 8 intersection points. Therefore, you are adding 8 new regions. You have to, because now this graphic becomes really complicated. If you take a look, that's what happened here. Okay, so this coloring on the right hand is very messy. It's just nobody can reasonably just carefully enumerate all of them without making a mistake. But The left-hand side without the coloring, it just clearer because you are not counting how many times you cut into all the regions. You are counting how many times you can create intersection points. So therefore, in this problem with 5 circles, you add them up. This is 8 plus 6 plus 8. That's 22. You can add 22 regions with 5 circles. Okay? This is a difficult counting problem, but fundamentally, we're still kind of construct what we need to have at the end by adding circles and circles. But at each step of the way, you have to look carefully what is the essence for our adding. The addition is not based on, you easily say, this circle will cut into all the existing regions. That's not the case. Take a look. If you look at this circle cannot possibly say this green circle did not cut into the original created, there's a region number 12, right? That way, it cannot cut into region number 12. This green circle, however, can intersect with all the 4 existing circles. There's no guarantee that each circle can cut every existing subregions. That's the essence of this problem. So you are really counting how many intersections it creates. And think about it. Each time it creates a new intersection point, it will create a new region. Because now, look at the green one. It enters one of the circles, make a cut, but that has not finished. It's only when you exit whatever region, current region you are in, that means that you are intersecting with another arc. It must be part of a circle. So you are really counting how many times this circle can enter into an existing region and then exit from that existing region. But that's the same thing. You count how many times it can enter an arc, then exit the arc. And finally, it's the same thing as how many times it can enter an existing circle and exit existing circle. That's the way a new region is created. And from basic geometry, we know 2 circles can intersect at most 2 points. And that explains why we are doing this recursive addition. By the way, if you want to say, I have 100 circles, how did you want to calculate this number? Well, it turns out that there's some recursive equation for this, right? There's an equation developed this n. Let's say an is the number of the region for n circles. There's a recursive equation describe this pattern, and we can solve that equation to get a general form for an and quickly get the number. But that's a totally different problem. That's an algebra problem. For this, and in Mathcounts, I guarantee you will never have this type of problem. Because if that's the problem, it's way more advanced than at the Mathcounts level. It will be an AIME problem. So that's it for today. I will see you next week. Bye.